Okay, David, am back. In this session, I will introduce you to a law, which you will be using to determine the rate of heat transfer for the conduction mode. Just to recap, below is a possible definition of conduction. Fourier developed a law, which is now widely used to calculate the rate of heat conduction. Q is the heat flow rate at a given position, determined by the value of x in the equation. It is the number of joules flowing per second, and is measured in watt. Check the equation out, you can see that the heat flow is proportional to the area, A. This is logical, because if the area is doubled, you would expect the heat transfer rate to double as well. From the equation, you can also see that the rate is proportional to the temperature difference over a small distance, dt. You could expect this, as the temperature difference, between 2 points, can be regarded as the driving force for heat transfer. You would then expect a higher heat transfer rate for a higher temperature difference. You can also see that the rate is inversely proportional to the change in a small distance, dx. You could expect this, because if the distance, over which a temperature difference occurs, is reduced, you would expect a higher heat flow rate, not so? K is the proportionality constant, known as the thermal conductivity of the solid, or stationary fluid, through which the heat is being conducted, and it is measured in watts per meter per Kelvin. The negative sign in the equation is multiplied by the slope of the temperature. The slope of the temperature is negative, so Q ends up being positive in the x direction. Values that you will encounter for conductivity, or K, in Fourier's law, are given in this slide. If you look carefully, you will see that the thermal conductivities of gases are low. Can you think of a reason for this? What do you say? In a gas, the molecules are far from each other, so the opportunity for them to bump against each other is less than for a liquid or solid, hence the conductivity, and hence the heat transfer rate, will be lower. For liquids and solids, the molecules are progressively closer together, resulting in faster heat transfer, and hence resulting in a higher thermal conductivity. If you look further, you will see that metals have the highest thermal conductivities. Why do you think this might be? A metal structure consists of positive centers, surrounded by a sea of electrons. Why would this result in high heat transfer rates? If you said that heat is transferred by the electrons, which can whiz around faster than molecules, you are correct. In this slide, you will be looking at how heat flows through a solid flat plane, such as a wall, from the one side, at x1, to the other side, at x2. The wall has a height of h meters, and a length of b meters. The one surface of the wall has a temperature of T1, and on the other side, the other surface of the wall has a temperature of T2, over here. The finger showed you the surface where you would feel a temperature of T2. Throughout the thickness of the wall, you have a temperature gradient, with the temperature ranging from T1, on the big surface facing away from you, to T2. The temperature inside the brick wall, will be between T2 and T1. On the right you have Fourier's law. The heat flow, Q, for the wall is distributed over the whole heat transfer surface. All heat flows must be added to obtain Q, the total heat flow. This is shown in the next two animations. Heat will flow from the high temperature, T1, to the low temperature, T2, across the whole of the cross-sectional area of the wall. This cross-sectional area is perpendicular to the direction of heat flow. This area of heat transfer, A, in Fourier's law as shown on the right, is constant from x1, where the temperature is T1, to x2, where the temperature is T2. It has the same value as the area you felt with the finger, and is equal to B times H.